I also work in motivic commutative theory. Let's see. Oh yes, this button.
Yeah, we can see your screen now.
All right, that's great. So, I mean, as the title says, I want to tell you about power operations in normed motivic spectra. And I should say in advance that this is a reported work in progress. It has been in progress for quite some time now, but it's still not written up in any way completely. And it's a joint work with Ernel Manto and Jeremiah Heller. Yeah, okay, so let's get started. So my plan is, right, so I realized that the title is quite long and has many fancy words in it. So basically I want to answer 3 questions in this talk. What's a normed motivic spectrum? Then what's this power operation which I'm talking about, or these power operations? And then of course, what's the point of it all? Okay, right, and of course ask questions at any time. I should say this is my first online seminar, so well, we'll see how it goes. You'll be to judge for that, I suppose.
Right, and I should say also that it is also the obligation of the audience members to not be afraid to interrupt Tom when they have questions. We have to, as audience members, we have to be a little bit more sort of assertive with our questions, asking our questions than in a traditional seminar. Okay.
Right, I can't see any of you already, so it's difficult. Okay, so first of all, well, this normed spectrum business has got something to do with highly commutative ring spectra. So let me first maybe remind you what an E-infinity ring spectrum is in the classical sense, probably more for my benefit than for yours, since you're, I mean, yeah, so I'm not very classical, so this is somewhat strange to me. But all right, so here's one way of presenting E-infinity ring spectra in the classical sense, maybe slightly idiosyncratic, which is you consider this functor, which I call SH upper tensor, and it goes from the category of spans in finite sets to the category of infinity categories. So where a span is just some sort of roof, right? So the category of spans of finite sets, this is a 2 category in which the objects are the finite sets, and the morphisms are these little roofs, right? So morphism from X to Y is a finite set Z together with a morphism to both X and Y. And then there's some composition there, which is with a pullback and so on and so forth. And this is, well, it's not a strict, so it's not because sort of pullbacks are not strictly functorial, you get a 2 category and not a 1 category. But all right, we can deal with that. There's also even infinity categories around, so we better be prepared to understand this. And so what does this functor do? Well, certainly for every finite set, it has to give you a category. And the category is just what I would denote SH upper X. This is just the category of functors from X viewed as a discrete infinity category with like almost no morphisms to SH, or in other words, it's just a finitely copy of a product of finitely many copies of SH indexed by X. No big deal. And then of course it's supposed to be a functor. So for every morphism between finite sets, you have to have a pullback and a push forward. And well, I mean, that is a very classical thing. The pullback is just, well, pullback, and the push forward basically is the indexed smash product. So in particular, if you consider the map from sort of 2 points to 1 point, then an object in the source is just a two spectra, and then the push forward is just their smash product. Okay, and then so this functor, we can model, for example, these infinity categories as quasi-categories, and then this functor, it's going to be classified by a co-Cartesian fibration, so by a certain map of simplicious sets. And then it makes perfect sense to just talk about the simplicious set of sections of that thing. So this gives you a new infinity category, which I denote by sections of SH upper tensor. And so the objects are, well, there are some families of spectra, right? For every finite set X, you have to produce an object EX, which is going to live in SH upper X. And then for every morphism between finite sets, you have to have these comparison morphisms between the sections, so and so, between the values EX and EY. And so there's a full subcategory of this thing, which we denote CH of SH. This is the category of E-infinity ring spectra, and the category consisting of precisely those sections such that the comparison map for the pullback is an equivalence for every map between finite sets. And of course, I mean, there's this other comparison map, which basically says it can multiply together. So there's a map from the indexed smash product of EX down to EY. And so that's some sort of multiplication map. And yeah, so somehow this encodes a lot of higher structure, and this is what people call an E-infinity ring spectrum. And I mean, as you can see, it's probably pretty hard to write down these things on the nose, but all right, so that's the definition. And so in particular, what you see is that, right, so a section, this consists of many spectra. But if it's a commutative, so if it's in C-algebra, an infinity ring spectrum, then really the section EX is just pulled back from the star, right? So it's really just one spectrum, and then there are these multiplication maps. The pullbacks are just bookkeeping. And so what this means is that you can just forget from C-algebra of SH down to SH by just sending this section to its value at the final finite set. And that's going to give you a functor, which I denote U. And so I think if this is sort of the underlying object, this makes some sense because it's clearly a conservative functor. And one can also show that it preserves limits and shifted co-limits. So then it's going to have a left adjoint. So this is somehow the free E-infinity ring spectrum. It's a lot like taking, I don't know, some sort of free commutative ring on a set. And it's denoted sim. And then there's a general formula for what sim does. And you sort of sim on any spectrum. There's a formula. I just want to point out that if you take the sphere spectrum, which is sort of the simplest thing which you could stick in, then you get something which, as sort of the underlying spectrum again, is a wedge index on the non-negative integers of the suspension spectra of the classifying spaces of symmetric groups. Okay, so this is maybe a bit random thing, but this is going to be important for what I'm going to want to do. Okay, so then let me describe the motivic generalization of sort of E-infinity ring spectra. This is also, so to speak, the naive motivic E-infinity ring spectra. So what we do in motivic homotopy theory is the following. We start with some scheme S. I mean, it might be the spectrum of the complex numbers or something scarier, but I mean, for lots of considerations, it doesn't really matter what it is. Then we're going to build a functor, which is called SH upper tensor lower fin S. And it goes from the category of spans in a category which I call fin S to infinity category. So it's looking a lot similar. And the category fin S is going to be the category of finite disjoint unions of copies of S. And we view this as a full subcategory of the category of all S schemes. And then you see, of course, this is slightly silly because this category is equivalent to the category of finite sets again. But I hope it will make sense soon. Okay, and so what does this functor do? Well, so certainly every scheme X is going to be sent to what's called the motivic stable infinity category of X. Well, so if you don't know what this is, here's the definition. I'm not sure how helpful this is going to be, but what you do is you consider the category of smooth X schemes, and then you pass two presheaves of spaces on that thing. And then you perform two localizations, which basically make the affine line contractible and invert something called Nisnevich hypercovers. So that's some presentable infinity category. And you pass the pointed object, still a presentable infinity category. And this has a symmetric monoidal structure coming from the smash product. And then inside that category, there's this projective line, one of our favorite motivic spaces. And what we want to do is we want to consider a category where smashing with this projective line is an equivalence. So there's a universal way of doing this, and that's what the motivic stable homotopy category, stable infinity category is. Of course, again, this is supposed to be a functor. So also you have to explain how the pullback and the push forward works. And so that's for any morphism between schemes, there's a well-known pullback operation just coming from pullback of schemes. And here the push forward operation is so the point is that since this category of finite fin S is equivalent to finite sets, producing this functor SH tensor lower fin S is basically the same thing as providing a symmetric monoidal structure on the category SH of S. And this symmetric monoidal structure, of course, is the one which comes from the smashed product of motivic spaces. So again, the push forward is basically some indexed smash product. And then you just do exactly the same thing as before, right? So you can form the category of sections of this weird functor, and you're going to ask, so we're going to look at those sections which are somehow Cartesian over this backwards arrow, so where it's really only one spectrum with some multiplication maps on it. And that's the category of motivic E-infinity ring spectra. Totally no problem. And again, we can just forget down from the motivic E-infinity ring spectra to just motivic spectra. It's going to have a left adjoint for formal reasons. And again, there's a formula for what this left adjoint is in general. And again, I want to just point out, if you apply this to the unit, then we get something which looks very similar. So we get, again, a wedge of suspension spectra of classifying spaces of finite groups, but this time it's a so-called Misnevich or naive classifying space. So I don't want to really explain what this means. It's just that in motivic homotopy theory, as in, for example, equivariant or global homotopy theory, there's somehow several notions of classifying space. And the Misnevich one is sort of the most naive one which we could do. And I mean, in fact, it's very easy to deduce the formula on the left from the formula on the right or the other way around. So it's basically the same information. Okay, so now there's going to be something better. That's basically the whole point of my talk, that you can do better than this. So there's a theory of so-called norm spectra, which we worked out some beginnings of this theory with Mark Oyoa, and then I guess this project with Eldon and Jeremiah is some continuation. So to explain this for your convenience, I left the definition of motivic E-infinity ring spectra on the left-hand side, and now on the right-hand side we do something slightly better. And so the first step is that we had this functor, SH upper tensor lower fin S, and we are going to extend this over a bigger category, and then we call it SH upper tensor lower smooth S. And so the source category is now something which I denote by spans on smooth S, all, fed. And so what this means is it's a new category spans where the objects are all the smooth S schemes, right? So before we only had the finite disjoint unions of copies of S, but now we allow all smooth S schemes. That's many more. And the morphisms are still spans, of course, but now you're not allowed to just use any kind of roof. You have to use a roof where the forward arrow is finite et al. So this is, for example, if you take, well, a finite disjoint union of copies of something and then map it down to the original thing, that's a pretty dumb version of a finite et al map, but there are more general ones, something like field extensions in characteristic 0 and that sort of stuff. And so in order to explain what this, well, I mean, I won't be able to explain in detail what this functor does, but I mean, of course, you need to have pullback and you need to have this push forward. And so this push forward is this functor which we denote P lower tensor, which has to be defined for every finite et al morphism. And so we denoted P lower tensor because it has something to do with smash product. For example, it's a symmetric monoidal functor. And so part of the work with Mark was to make sense of this functor, and it basically comes from an operation in algebraic geometry called Veil restriction. It doesn't really matter for our purposes exactly what it is. But there is somehow some indexed smash product in the motivic world, which is more general than just indexing on finite sets. You can index somehow on finite et al extensions. Something. Okay, and then we can basically repeat the same story as before. There's a category of sections of this functor. And now, of course, giving a section is even more data, but okay, let's suppose one could do this. And then we can again consider this full subcategory where it's really only one spectrum with some sort of weird multiplication maps. So where so looking at those sections which are Cartesian over the backwards morphisms. And so this category we denote by NH of SH of S. So the N stands for normed. And this category is supposed to be an improvement of the category of E-infinity ring spectrum. For example, there's a forgetful functor from NH to CH. And then, of course, we can further forget down to just motivic spectra. And again, for formal reasons, there's a left adjoint, which is denoted NSIM. You can see we have a clever naming convention there. And so it took us quite a lot of pain to figure out what this NSIM thing is. But Mark and I, we managed to prove that there's a formula for there's a formula in general, but it's quite complicated. But if you stick in the sphere spectrum, then it looks quite reasonable. You again get a disjoint union of suspension spectra of classifying spaces of finite of symmetric groups. But this time you get something not the naive or Nisnevic classifying space. You get something fancier, the so-called étale classifying space. Again, I won't be able to explain in detail what this means, but I guess the étale classifying space or geometric classifying space, this was somehow invented by Totaro and then further studied by Morel and Wojwocki, and somehow this is the best version of, well, whatever their best means, but it's a much better version for some things than the Disneyevich classifying space for reasons which I hope will become apparent. Okay, right. Okay, so that's the definition of a norm spectrum, or as much of the definition of a norm spectrum as I want to give for the purpose of this talk. And now we come to power operations. So this was basically the review of the paper with Mark, and now is the actual new stuff. So first of all, let me remind you how to build, well, one way of building power operations classically, and then we're going to try and do this motivically. First for the motivic E-infinity ring spectra, and then for the norm spectra. So classically, you do roughly the following. You start with an E-infinity ring spectrum, which is in fact an algebra over the cohomology, let's say with sigma 2, the Eilenberg-MacLane spectrum, H sigma 2. Of course, you can do this for other primes as well, but our work is at the prime 2 only, because you have to start somewhere. And suppose that we have some map alpha from the sphere spectrum into just the underlying spectrum of E. So in other words, we just have some element alpha in pi 0 of E. And then what we can do is, well, we apply this sim adjunction, of course. And since we're also an H sigma 2 algebra, we can then further smash with H sigma 2. So we produce a map sim of alpha, which, well, it starts at this H sigma 2 smash sim of 1. And it goes to E. And then we're going to try and do something with that. So you should remember that the sim of 1 was this union, this co-product of classifying spaces. And so, well, what you need to do is you need to figure out sort of what the cohomology or homology of classifying spaces of the symmetric groups is. So in particular, we're going to focus on the sigma 2. The 2, there's a sigma 2, there's a 2 for the sigma 2, and the 2 for the H sigma 2, and they're the same 2. But in any case, so what is possible is that one can figure out that this B sigma 2 smash H sigma 2 is just splits into a vector shifts of H sigma 2 indexed on the non-negative integers. And so what we can do is we can look at one of these cells and just consider the composition of the sim of alpha map with the inclusion of the cells into this B sigma 2 smash H sigma 2, and then we include that thing into sim of 1 smash H sigma 2. And so what we've done then is that we've produced, right, so a family of new maps, this going from some shifts of the sphere spectrum into this underlying thing of E. Or in other words, we've produced some new elements in the homotopy groups of E, in the higher homotopy groups of E. And so we started with something in pi 0, but there's sort of well understood methods / tricks / whatever you want to call them, where you can do this in general, you can start in any degree. And so this is what the power operations are. Basically, there's some operations from the homotopy groups of E to the homotopy groups shifted a little bit also of E. And then you can study their properties in detail, and they have many interesting properties. So for sure, they're like natural in ring morphisms in E, and so on and so forth. I don't want to bore you with this. Okay, so now we try to, yeah, and so I should say that, well, this again, classical topologists probably know this better than I do, but you can use these to prove very interesting results. And in the last section, I'm going to try and explain some of the results which I can prove with this. Now let's try to do this again motivically, and let's first try to do this for this sort of naive motivic E-infinity ring spectra. Okay, let's just try to do the same story. So we start with some some motivic E-infinity ring spectrum, and again we should let this be an algebra over some sort of Eilenberg-MacLane spectrum, and there are various things which you could call Eilenberg-MacLane spectra in motivic homotopy theory, but there's one thing which is even older than motivic homotopy theory. It's called the motivic cohomology, and so this is also representable in the motivic homotopy theory category by something which we also denote H sigma 2, and I feel like that's a good thing to start with. That's a good thing to try. So, and then we can also prove that this motivic cohomology spectrum is an E-infinity ring spectrum, and so on and so forth. It's not so problematic. All right, so let's just write down this line. Let E be an H sigma 2 algebra, and let alpha be in pi 0 of E, just as before. And then again, by adjunction, we extend this over the free E-infinity ring spectrum on the sphere. And right, so then if we want to do the same thing, what we need to do is we need to compute the motivic cohomology of this Disneyevich classifying space. But it turns out that it has exactly the same answer as classically. And again, this is basically equivalent to the classical statement. It's an easy consequence of the classical statement, and it also implies the classical statement. So this means that we can do exactly the same thing as before and produce some power operations, right? And so there again, they land in shifts of alpha. So they land in sort of in higher homotopy groups. Now, one of the things in motivic stable homotopy theory is that we have two spheres, at least, right? So we inverted this P1, this projective line, and it turns out that this itself, it splits into a smash product of two things, one of which is called S1 and the other is called GM. So in fact, there's sort of two things which have been naturally inverted. So this implies that your homotopy groups are going to be bi-graded. And so what this power operation does is somehow it changes the index corresponding to S1, but it leaves the other index basically alone. I mean, that's just a fact. That's what it does. That's what you construct. So we've constructed this operation, at least sort of starting in 0, 0, and you see that that's exactly what it does. And what I'm going to argue is that this feature is like a big problem. Or, I mean, for some things which you want to do, this is a problem. So now let's see if we can instead do this for non-motivic spectra, and maybe we can cook up a better power operation. So again, on the left-hand side is the definition for motivic infinity ring spectra, and on the right-hand side we're going to try and do a generalized construction. So what we want to say is, okay, let's start with a norm spectrum, which is in fact an algebra over H sigma 2. But so the first problem which you run into is saying, okay, how do we produce any norm spectra whatsoever? In particular, so writing down some E infinity ring structure on some spectrum is highly non-trivial thing to do in general. So how do we know that H sigma 2 is one of these norm spectra? Or I mean, how do we put a norm spectrum structure on H sigma 2? And I mean, that's a fair question, and it's not so easy. But again, Mark and I, we managed to do this, in fact, in several ways. But so the answer is that we're just gonna accept this paper with Mark as things which we're allowed to assume, and in there you can find a theorem which tells you that indeed there is this canonical structure.
So Tom,
yeah,
you just said that you showed that H mod 2 is a norm spectrum in several ways. I assume you meant you gave several proofs, or
yes.
Okay, I assume there's like a unique norm structure.
There is at most one norm structure on it, which is with, I mean, there's exactly one norm structure on it, which is compatible with the structure as a homotopy commutative ring spectrum.
Okay, and also maybe this is the sphere spectrum, is that known to be normed? That's
yes.
Okay. All right.
Yes. Yeah, so lots of spectra are known to be normed. The sphere spectrum, then sort of algebraic cobordism, special linear cobordism, that sort of thing, algebraic K theory. So many reasonable things are not, but it's not so easy to prove. Okay, so we're allowed to write down this first line, which we started with, so that's a good start. And then again, by adjunction, this is the same formal nonsense argument as before. We can extend this over the free norm spectrum. And so the next thing which you have to do is you have to figure out what the motive is of the classifying space, the étale classifying space of sigma 2. But so the advantage is that, well, we don't have to figure it out because Wolwatzki already did. So he computed that, well, I mean, right, so there's always this base scheme, and then there's some mild assumptions on the base scheme probably which you need to put in there for these statements to be correct. But I'm never going to mention this. This is going to be true in a large number of cases. There's some problems with something like if 2 is not invertible in your base, then something might be problematic. Anyhow, right, so you need to compute this thing, and which is great for us, is that Wolwatzki did it. And so what happens is that the motive of the étale classifying space again splits into a wedge of things indexed on the non-negative integers. But now you don't just get a shift, you get something called a twist. So basically you get a smashing with this other sphere. And so this, well, I mean, it depends on how you index your spheres, but basically this twist goes up sort of by half the speed of the shift. And well, then there's like an obvious thing which you do. You still include one of the cells, and this way you've produced a new element. But right, so this new element now doesn't just start at the shifted sphere, it starts at the shifted and twisted sphere. And so this, again, you can extend, right? So we've explained what to do sort of for alpha in pi 0, 0, and there are some tricks which you can play in order to do this in arbitrary degrees. And so you cook up a power operation, and it changes the degree, just as the old one, but it also changes the weight in a predictable fashion, but it definitely does something else than the old power operation. In particular, it has to be different in general. Well, I think the only way which they can be the same is if they're both 0, right? So, okay, so this is some new thing. Right. So let me give you an example right? So this is a formal nonsense thing which we've done, and it looks maybe pretty scary, but let me show you that it's not, at least it's not entirely insane. So what we can do is the following thing. So let's say we take some smooth S scheme X. Well, this doesn't really have to be smooth, but for simplicity, let's do that. All right. And then this is going to have a suspension spectrum. Sure. And then what I can do is I can form the internal mapping spectrum from this suspension spectrum to HC mod 2. And so this internal mapping spectrum is going to be some new motivic spectrum, and this operation is a right adjoint to this mesh product. And so what one can do is one can show that this internal mapping spectrum acquires a natural normed structure, and in fact this structure of a normed spectrum, sort of an algebra over HC mod 2, or under, I don't know. Right, so basically this comes from the fact that you're mapping out of a space which is sort of co-normed in a sense which I don't want to make precise, then, right, so it's exactly the same sort of reasoning as in classical topology. And then what's going to happen is that the homotopic groups of E are just the same thing as the motivic cohomology groups of X. I mean, that's just the definition of internal mapping spectrum and motivic cohomology, I guess. And so what you see then is that you have this power operation, right, acting on the homotopic groups of E. And you can translate this into something acting on the motivic cohomology groups of X. And it turns out that if you look at Q minus I, this has exactly the same degree as some other operation, which is well known, the so-called motivic Steenrod operation, which Wojewodsky constructed and used, of course, very effectively in his proof of the Milnor conjecture. So they have the same degree. So it seems like a reasonable question what the relation is. And in classical topology, these two things which you can do are exactly the same. And it turns out that also in the motivic world, again, this abstract power operations business is exactly the same thing as Wojewodsky's motivic Steenrod operation. And in fact, this is not a deep result at all. Because if you look at Wojewodsky's paper in the motivic power operation, so what he says is that, well, we will try many things to construct this operation, and basically in the end we've come up with the following, which is just what you would get if you take the definition of power operations in an E-infinity ring spectrum and do it motivically. And yeah, so this is entirely true, and so basically Wojewodsky's definition is the same as our definition. It's just phrased more abstractly. Right. So I get the feeling that I'm talking a bit too fast, but so that's okay. So that's the construction of the power operations.
Yeah, Tom, that's okay. We're flexible about exactly how the schedule goes.
Sure.
And yeah, that's no problem.
And so okay, so that's the definition of the power operations, and you see it's not entirely unreasonable. And so we come to the final section, which is basically, so what? Who cares? So in order to sort of explain why I care, yes, okay, so the point is I care. That's why I've been spending like a year trying to write a paper which says that all of these things work. But in order to explain why I care and explain why I hope you might also care, so let me remind you of some classical results. So classically, there's a theorem. I mean, I don't even know who to attribute this to, but okay, so it's a fact. That if you look at this dual Steenrod algebra, right? So just look at the homology of HC mod 2. So this is going to be some ring. And of course, I mean, HC mod 2 is an E-infinity ring spectrum. So its homology is going to carry power operations. So this is a ring with power operations. And it turns out that this ring is it's pretty small. I mean, it's of course pretty huge, but in some sense it's pretty small. And it's pretty small in the sense that it is generated under the power operations and the ring structure, of course, by the Bachstein. So what this means is you have like the unit and you have the Bachstein, and then you add some things together, you multiply some things together, you apply some power operations, and you keep doing this. And if you do it in a clever way, you can hit every element whatsoever. So this, I guess, is a computation. If you know how to compute things, in particular, if you can figure out somehow how the power operations act on your description of this dual Steenrod algebra, then you can figure this out, I assume. Well, I mean, it must be possible, right? And so, again, why is this relevant? And probably the topologists here know better than I do. But so these sorts of things, they typically imply kind of splitting results by sort of Milnor-Moore arguments. So there's one thing which you can prove from this, It's what I would call the E infinity workless theorem. Maybe I'm going to explain in a bit why I would call it that. So the statement is, well, you can read it, is that if you take a E infinity ring spectrum, and then it's pi 0, that's of course just the commutative ring in the usual sense. And I'm going to assume that this ring, pi 0 of E, has characteristic 2. And then I say E has characteristic 2. And so it turns out that just under these assumptions implies that E is a module over HC mod 2 over this Eilenberg-MacLane spectrum. And so this has, of course, a huge number of consequences. For example, classically, a module over the Eilenberg-MacLane spectrum is itself Eilenberg-MacLane. It splits, of course, then into a wedge of some shifts of this Eilenberg-MacLane spectrum. Also, it, of course, implies for more formally that the Hurewicz map from the homotopy of E to the homology of E also splits. And then you can prove a huge number of things with this. Okay, so it's just the point that homology is so much easier than homotopy that allows you to do a lot of good things. And okay, so this is a sort of laughably weak result because there's an actual workless theorem which replaces E in C-alge of SH by E in C-alge of the homotopy category of SH. So, right? So if you just take a homotopy commutative ring spectrum with the same assumptions, then the same conclusion holds. So that's much stronger and also quite a lot more difficult to prove. But okay, so here's the weak theorem, which I think is also interesting. So then let's, right, so there's this philosophy basically that every result in classical homotopy theory is somehow mirrored in motivic homotopy theory. So of course the same thing has to be true, right? So let's try and prove that. And so what you do is this, okay, let's try to prove that the motivic dual Steenrod algebra is generated by power, we have the power operations, right? The naive power operations, there should be good enough. It should be generated by the Box-Steen. So first of all, you have to compute the motivic dual Steenrod algebra. And again, in reasonable cases, this can be done and was basically done by Wojewodsky. And so it turns out that this motivic dual Steenrod algebra, it's quite similar to sort of the dual Steenrod algebra in odd characteristic, basically. And so it turns out that it's essentially sort of a polynomial ring in two families of generators called tau 0, tau 1, and so on, and psi 1, psi 2, and so on. And then there's some relations which, I mean, also they're not terrible. I could write them. It's just that I ran out of space there, but it also doesn't matter. And so what happens is that these tau i's and psi i's, except for tau 0, they have positive weights. So the weight is the second star, so the second degree, so to speak. And also the coefficients have non-positive weight. So now, could it be possible that this thing is generated by the Box-Steen on the power operations? Well, I mean, just suppose, right? So you have the unit and you have the Box-Steen, and they're both of weight 0. And then you're allowed to add some things and multiply some things and multiply by the coefficients. You're still in weight less than or equal to 0, right? And then you apply your naive power operations, and we said it doesn't do anything with the weight, so you're still in weight less than or equal to 0. So if you keep doing all of these things, you're never going to hit like tau 1 or, I mean, any of the generators, because they're all in positive weight. It's impossible to reach it. So, okay, the first theorem, unfortunately, is false. But so the consequence could still be true. We just have to come up with a better proof. Okay, but it's also false. So let me show you an example. So let's say we just take the base scheme, the spectrum of the complex numbers, right? So then algebraic, then the smooth S schemes are basically algebraic smooth varieties over the complex numbers. So that sounds like a very reasonable thing to think about. And so it turns out that the sphere in the motivic world has a famous endomorphism, which is called, well, the motivic Hopf map, and it's called eta, and it's a non-nilpotent endomorphism, a graded endomorphism, so to speak. And I suppose Morel figured out maybe that this thing is non-nilpotent, and in fact, what he did is he computed the zero-stable homotopy group of the mapping telescope of eta. I mean, he also computed lots of other things, but in particular, he computed that. So he tells us that the pi 0 of the eta inverted sphere is the Witt ring of your base field. And if that base field happens to be the complex numbers, or, well, okay, so if it happens to be the complex numbers, then the Witt ring is well known, it's just Z mod 2. So in particular, this eta inverted sphere, this is an example of an E infinity ring spectrum, because, I mean, the sphere is an E infinity ring spectrum, you invert something, it's still E infinity, and it has characteristic 2. So this E infinity Wörgler theorem would have to apply. So what should happen, certainly, is that this Hurewicz map on the Ada inverted sphere, it should split. And then, I mean, as a topologist, you should object to this, right? Because Ada, if it's has anything to do with a thing which is called Ada in topology, then it should be 0 in homology. So this means that the homology of the Ada inverted sphere should be 0, and then for sure it shouldn't split, because I just told you that it's not the zeros. The Ada inverted sphere is not 0, right? And I mean, this argument is completely correct motivically. So Ada does vanish in motivic homology, and the Ada inverted sphere motivically is not 0. So it's just not the case. So this E infinity Wirkler theorem also doesn't hold motivically. Okay, so that's kind of sad. But, right. So now we come to the main point of my talk, which is that if you use genuine power operations instead, then these problems go away to some extent. So these are basically results which are hopefully going to be proved by Alden and Jeremiah and me. And so this is now, I put a star at the theorem to make it clear that I'm not claiming that this is like 100% checked, but we've written about 80 pages about how to prove these things, and we're very confident that it works. But well, okay, so there's something we're not 100% sure yet, but it's probably going to work. So what you can show is that this dual motivic Steenrod algebra, right? So we said that HZ mod 2 is a norm spectrum, so it also has genuine power operations, not just the naive ones. And it turns out that if you use these genuine power operations, then this generation results from classical topology still holds. And so what you might imagine is that then this E infinity Wirkler theorem should also work. And it turns out that indeed it does. So some version of that is true. Again, this is in some sense it's a formal consequence of this, right? So the second theorem is in some sense a formal consequence of the first one, but it's much more subtle than in topology. So you need some Milnor-Moore argument, but so in topology, Milnor-Moore is something about, I don't know, connected Hopf algebras over a field, and in our case, well, it's not going to be over a field, it's going to be over the coefficients of motivic homology, which is some graded ring, and so you have to somehow make this work, but then you can use some sort of graded Nakayama, or you can try, and then also sort of you want it to be connected, but there's not sort of no obvious notion in which this thing is going to be connected. So you have to very carefully keep track of sort of the degrees of various elements in order to make sure that there's some sort of vanishing line which allows you to say, well, okay, so at some later point we're going to make this argument available, but so it's much more subtle than I would like. But in any case, we think we can prove this. So we can prove that if you take a norm spectrum of characteristic 2, then it's your Ravitch map splits. So then you can of course try and draw some conclusions from this. For example, we can look at this Ada inverted sphere, and so for sure your Ravitch map does not split on that thing we just said. So the conclusion then is that it cannot possibly be a norm spectrum. So this is something interesting going on here. You start with a norm spectrum, you invert some element, you're not a norm spectrum anymore. Okay, so I mean, I guess this is a familiar phenomenon also from equivariant homotopy theory, but okay, yeah, so similar things happen motivically. Quite fun. And you could also ask, what if you take somehow a better version of inverting elements, right? So there should be some formal nonsense way of inverting the sphere Ada in a norm spectrum. So could that be something interesting, right? But it turns out if you look at the same argument, right, if you take any spectrum, any norm spectrum E, which inverts Ada, let's suppose it's characteristic 2, which is not a strong assumption, right? So then the argument as before is still going to apply, right? So the homology is 0, but then by the theorem, the homotopy has to inject into the homology, so the homotopy is also 0. So this tells you that any way of invert, right? So the only norm spectrum which can invert Ada is actually the 0 spectrum. So this would be a kind of fun application of the theorem of Alden and Jeremiah and I. So unfortunately, as you can see, as an example of Mark and I, because you can prove this more directly using sort of different methods. And yeah, so in general, unfortunately, I don't know any interesting applications of our theorem yet, because there just don't seem to be a lot of motivic norm spectra of characteristic 2. I guess also this theorem tells you why there are not so many, but yeah. So I mean, for example, classically there's some like MO, which then in some surprising miracle splits into HC mod 2s, and we don't yet have any analog of this kind of miracle motivically, but I guess this theorem would at least make it possible to get such a miracle. Yeah, and I think that's all I want to say.
Okay, and let's start with some questions. I've got a few lined up, but I'll let other people go first. Yeah, Kirsten.
So there's, in the G-equivariant world, there's this lattice of different numbers of norms that folks like Luis Pereira and Hill and Blumberg all think about. Here you've got genuine and naive. Is there any analog of the things in between?
Yes, there are definitely analogs of the same ideas and questions. So, I mean, so one thing which controls how many norms you have is basically over which category you extend this SH tensor functor, right? So I chose to extend it over all smooth schemes and all finite étale morphisms. And you can extend this over other categories of spans. So for example, instead of taking all smooth schemes, you can take all finite étale S schemes. This will also give you a notion of a norm spectrum, and it's strictly weaker. So that's one thing which you can do. This is not directly analogous to these incomplete norms of Hill and Co. And I don't quite know how to encode these in terms of spans and not operads, but I'm pretty confident that something similar should be possible. Yes, so we have explored something like this. We have explored some variation, and it seems that taking the smooth schemes is somehow has the best formal properties. For example, then the norm spectra are stable under arbitrary base change, which is not true in, right? So E-infinity ring spectra are also stable under arbitrary base change, but if you take, for example, just finite étale things instead of smooth things, then this is not going to be true. So somehow this seems to have the best formal properties. And if you try to take a bigger category, then you get other problems. So this seems to be the best, but there are notions in between which could be explored. Yeah.
Is it naive to hope that you'd get more power operations looking at the smaller ones? Like, you know, you have these computations of sim1 in terms of B of, B-nis or B motivic, B étale of symmetric groups. I mean, you could hope that the computation of sim1 was interesting enough that actually you'd wind up getting different operations if you chose different norms. But maybe they're just some subset because there's some natural map or something.
Right. I mean, you can forget from a norm spectrum in my sense to an incomplete norm spectrum in the other senses. So to some extent, this suggests that the answer is probably no. But I mean, I don't think it's impossible. It might still happen. It would be a bit surprising, but I think it's possible.
Hey Tom, this is Kyle Ormsby. I was wondering whether you guys have thought at all about an operatic approach to these norm spectra, whether there might be some kind of operad where it's indexed on finite étale schemes instead of natural numbers. Is this in the works?
Well, I mean, we've definitely thought about it unsuccessfully. I mean, so one of the things which you have to take into account is that basically you definitely have to change the definition of operad for this to be possible. So even in the equivariant world, I mean, so there's a notion of sort of an operad acting on some category, and then you can do algebras under that. And even in the equivariant world, you cannot produce G-invariant and sort of G-commutative ring spectra from an operad acting sort of in the classical sense. That's just not possible. So you can do something which looks very much like that, but basically you have to change the weak equivalences on the categories of operads in order to take into account these graph subgroups. And this, I mean, basically it's a new category as far as I'm concerned. And so you have to invent some sort of notion of genuine motivic operad in order to do this. And yes, part of the hope with the paper with Eldon and Jeremiah was to do this. So you can, there's this characterization of E-infinity sort of operands of infinity operands in terms of polynomial functors. And so basically you can relate this with some sort of notion of symmetric sequences. And there is something like that which you can write down motivically using genuine motivic equivariant homotopy theory and lots of different and difficult things. And we were hoping to do this, but it didn't quite work out. And I think it's not going to be in that paper. But so things can be done, but they seem quite hard. But yeah, there's something which can possibly be done.
Other questions? All right, so my question is that, one of the possible applications of these QI operations is, I forget exactly how this works, right? But this is sort of, there's a proof of the Nishida-Nilpotence theorem that uses these QIs. And I seem to recall having tried to do this motivically with the naive QIs. And it didn't work because, basically that theorem that you had about how everything is generated under power operators by the box, and that's not true if you use the naive ones, as you can say, right? So I wonder if that, or this isn't so much a question as is like a suggested problem or project for someone, which someone should go back now and look at the classical proof of the Nishida-Nilpotence theorem and use these genuine QI operations and see what does or doesn't work. I mean, it can't exactly work because Nishida-Nilpotence fails motivically, but something like one should see what you can extract from that line or where it breaks down or whatever. And I wonder whether, and this is relating to this business about inverting eta, right? That the inverting eta was causing things to not be normed, right? And so I wonder whether it's true that if you take any non-nilpotent element in the motivic stable homotopy groups and you invert that thing also can't be normed.
Okay, I mean, for the first question, yes, I think this is very reasonable. It's definitely been on my to-do list, but I have not managed to look at it. Yeah, but I think this is definitely very interesting, and I would hope to do it at some point. So about inverting other non-nilpotent elements, I mean, I don't know. I don't really have a good understanding as for why somehow inverting something motivically, I mean, in this normed sense, why this kills things. So this project with Alden and Jeremiah was an attempt to sort of understand why inverting eta kills everything.
Yeah, sure.
I mean, I would not claim this part of the project to be very successful, so I still don't think I understand why this really happens. So I have no idea what happens with the other non-nilpotent.
Yeah, sure, and I don't really either, but I'm just kind of trying to fit it. I mean, the fact that Nishida-Nilpotence theorem must fail somewhere is sort of making me think that, oh, it must be like in that normed hypothesis, something's not normed. So, or something, anyway. The other thing that I would say, this is also sort of a suggestion. You made a comment towards the end about how maybe, what other things could there be that might be normed, right? So here, let me throw out one possibility. So we now know at least so first of all, this is only C-motivic, and so that might not be that interesting to you because it's not very arithmetic. But in the C-motivic case, we now have a motivic modular forms spectrum. And that ought to be as well-behaved a spectrum as one could possibly have, right? So I have no particular reason to want to know whether or not MMF is normed or not, but it just seems like something that, someone ought to look at.
Yeah, I mean, I totally agree. There's certain natural spectra which one should prove are normed, like motivic Morava E theories and possibly also MMF.
Those are good ones too.
Yeah. So I mean, I've not tried it. It's a great suggestion. I agree.
Okay. Are there more comments or questions? All right. Well, I'm going to unmute everyone again so we can thank Tom one last time. So thanks very much, Tom. And we'll meet again in 2 weeks for the last seminar of the semester. And I'm drawing a blank on who's speaking next week. Sorry, I didn't remember that. Anyway, we'll see you guys in a couple weeks.